All right, so once again, we're moving towards forces. We talked about centripetal acceleration before, and this time we're talking about centripetal force. Now, again, according to Newton's laws of motion, the only time an object will accelerate, in other words, change velocity, so if it's not moving, it'll move, and if it's moving, it'll move differently, is when you got a force exerted on it. And so, as we talked about earlier, is that a centripetal acceleration is always directed towards the middle. So you see my diagram here, and you've got your different velocities showing it. But again, if you're accelerating towards the middle, that means your force is directed towards the middle. So anytime that I'm doing these questions, I will not be referring to direction because, again, it's always towards the middle. Now, last class, we looked at centripetal acceleration. And we had three formulas, but I'm going to go with the simplest and the first formula we looked at, which was v squared divided by r, where again, v is your speed that your object's going around in a circle, and r is the radius, which again is from the center to the outside of that circle. Now, what I'm going to use is, and it's been used quite a bit, is Newton's second law. Oh, we don't need to be that big, which is F equals, Nigel, do you remember this one? Oh yeah, he's not here. F equals ma. So what I'm going to do is, if I want to find the centripetal force, I'm simply going to take my mass and times it by my centripetal acceleration, which is mv squared divided by r. All right, so there we go. And again, FC is the centripetal acceleration. Let me try to write that in there. Try some neat writing. There we go. That's your centripetal acceleration. Again, always directed towards the center. Now, again, I could take those other two centripetal acceleration formulas, and just by simply multiplying them by m, like I did this formula here, we come up with two more equations. So a centripetal force, you could say, is 4 pi squared. I can throw an m in there, rf squared. So again, all I did was take our centripetal acceleration formula, throw an m in there. I can do the other one. I can do the same thing, where I have 4 pi squared m r. And then again, this formula, the third formula we had was the period squared. So again, the radius is required for every single of these formulas, and also the mass is required now. All right, so but again, we can get away with having the velocity, having the frequency, and having the period to figure out our centripetal force. All right, so let's look at a couple of examples. Again, we got our 1, 2, 3 formulas, just as we had earlier today. We're going to do a little more than just substitute in here. So we have a 3 kilogram mass is whirled on a horizontal circle. So in other words, it's on a table, all right, on a frictionless surface by a rope that is 2 meters long. So right away there, it's in a circle. So I know I'm dealing with centripetal motion here, or circular motion. And so my radius is 2 meters. All right. What do we want to calculate? The tension in the rope if the object is traveling at 14 meters per second squared. So I'm going to throw that down. All right, meters squared, or meters per second, I should say, not squared, that's acceleration. All right, now it wants the tension in the rope. So this is an overhead view of our table, is that we have a center, and oh God, I'm going to try to draw a circle here with my mouse, but we'll give it a shot. Okay, that's a circle. Yikes. All right, I'm going to give that another go. All right, that's better. All right, so that is what we would call our circle. Again, our radius here is 2 meters. Now, that object is going in a circular motion because there is a centripetal force that is making it go in a circle. And what that force is supplied by, I should say, is rope. And so our tension, which again, I've said many times, just like when we did earlier today, with tension in the string. It is just the force applied by the string, or in this case, a rope. So our tension is equal to our centripetal force. And which, of course, if we want to find that tension or we want to find that centripetal force, we need the radius, which we have, and we either need the velocity, frequency, or the period. Well, we have the velocity. And so I'm going to use the formula FC here, that's a C, sorry about that, is equal to mv squared divided by r. All right, and so I'm going to substitute in my values. And so my centripetal force, again, which is the tension supplied by the string, the rope, the mass. Oh, I forgot to write that down here. My bad, because that's all I always write down my givens, because I hate doing this. I hate going back and having to look for things. All right, so my mass is 3 kilograms. My velocity here, whoa, I'm glad I put that in too. Look at me. All right, 14 squared. All right, and divided by my radius, which is 2. Again, notice everything is in standard units here. All right, and again, I'm just going to follow Bedmas here. So do an exponent first. So I get 3 times 14 squared. I'm thinking that's, I want to say 189, but I have no idea. Let's go to the calculator here. I won't say I don't know any idea. 196. All right. All right, and then, of course, my centripetal force. I just take 3 times 196 and then divide that by 2, and I'm getting a nice round number, actually. 294. We're dealing with forces, so we're dealing with newtons. There we go. All right, here's our force. 294. We're dealing with forces, so we're dealing with newtons. There we go. All right, so there's our centripetal force, 294 newtons, that keeps this moving on a horizontal circle, again, on a table. We're now going to look at a little bit of a different situation coming up here. All right, so let's see here. I'm going to try to anyways. All right, there we go. Example 2. A 5 kilogram stone is swung at a constant speed in a vertical circle. So it's a little bit different situation going on here. With a radius of 2.4 meters on the end of a rope. Again, we got a rope. If it takes 1 second to complete 1 revolution, all right, calculate the tension in the rope at, what's that? Oh, that's bad wording here, man. I've got some bad English here. Let's get rid of this because I'm doing that down here. So just a typo here. Calculate the minimum speed at which you can swing the mass while keeping it on a circular path. All right, so here we go. I'm just going to draw a little picture of what we've got going on here. This is a vertical circle. So again, I'm going to try to draw a circle. Not bad. All right. All right, now, so we're swinging this thing, and it has a centripetal force working on it. So there it is. I'm going to put my little FC in here. All right, and we want to know the minimum speed at which you can swing this thing and yet keep it in a circular path. Now, again, I'm going to write down my givens, which I didn't do before. I've got an R value here of 2.4 meters. All right, that's a big rope. It takes 1 second to complete the revolution. I don't think we're going to use that. I think I just added all this stuff when I shouldn't here. So I'm going to cross this out. I'm sorry about that. I'm going to change a little bit about this now. All right, but here's what we want to know is what is the minimum speed, right? Because if you've done this before, I think my last example, we're swinging a yo-yo around. If you don't swing it fast enough, it doesn't go. And in fact, at the very, very top, and that's why I've drawn this diagram, this is the point at which it will fall, right? If we don't swing it fast enough. Now, here's the thing in this situation, is that at this situation, the only thing acting on the rope, or on the rock, I should say, the stone we have here, is the centripetal force. And that only thing that centripetal force has to be, which we can't ignore, is gravity, is pulling it down. That's it. So all we need to do is have gravity act on the rope at the very top, and that will be the minimum speed that we can have. All right, now, what is our force of gravity at this situation? Because I'm going to look at the two extremes here. I'm going to look at the very top and the very bottom. of what happens. All right. So when I find the force of gravity, again, jeepers, mass is 5 kilograms, because again, when we find the force of gravity, it's mass times acceleration. And so I take my 5 times my 9.8, and let's put that in there. 5 times 9.8. And that's, I think, 49. It is 49. Beautiful. All right. So again, centripetal force is supplied by gravity. That's the whole key here. Our centripetal force is supplied by gravity. All right, which means then Fc, again, I'm going to use my formula here. What do I have? I have the mass. I want the minimum speed, velocity. And, well, I'm going to use the same formula I used last time, where we have mv squared divided by r. Now, again, our centripetal force is gravity. That's all we need there. So it is 49 newtons. Again, the mass of this stone is 5. Velocity, that's what we're trying to figure out. What is the minimum speed which makes this happen? Our radius is 2.4. All right, here. So now I got to solve. So again, I've mentioned this many times. I got a number equaling a fraction. I'm just going to go a fraction equaling a fraction on this one here. Okay, so that means I got to go, let's see, 1 times 5v squared is 5v squared. 49 times 2.4. I have no idea here. 49 times 2.4. 117.6. All right. I'm going to divide both sides by 5. And let's see here. I divide both sides by 5, and I get, whoops. Well, I'm just left with v squared on the one side. And on the other side, I take 117 divided by 5. I get 23.52. All right, and then obviously last out here, I got to square root both sides in the minimum velocity I'm getting. Let's see here, square root that number, and we get to 2 decimal places always, right? 4.849, so it's going to be 85. And again, my units are meters per second. So if your speed is any less with this mass and this radius of 4.85 meters per second, it will fall at the top. That's where you're going to find your issues are going to be, because that is the one extreme. It's at the very top where only gravity is supplying the centripetal force. Like I said, now at the minimum speed, what is the tension at the bottom of the string? So here's a different scenario. We're looking at the bottom. So here's our speed again. So I'm going to write that down because there's our minimum speed. So if this is what we're doing, we're wheeling around at the minimum speed because we don't want it to fall at the top, but we don't want to go any faster. I have a speed of 4.85 meters per second. Again, I'm going to write down all my givens. I haven't been doing good at that. So my mass again was 5 kilograms. That's like a 10-pound stone. All right. And again, my radius was, I'm not sure if I need all this stuff, but we'll figure it out. 2.4 meters. All right. Now, again, I said the situation's a little bit different. We want to know what the tension is in the string. All right. So I'm going to draw my diagram again. So here's their circular motion. Here's the center. All right. In the bottom, that's where we're looking at our object. All right. So the very bottom, we have a centripetal force in the end. All right. Now, what's happening here? So our net force, what's keeping this all together is that all we have working, we have a certain speed, which is creating a certain centripetal acceleration, which is consistent because we're going around the same velocity at the same radius. And so our net force is our centripetal force. Just like it was here, our net force was our centripetal force, but the only force we had was gravity for a minimum. But here we have something else going on. We do have gravity this time, but gravity is not pulling us towards the center of the circle. It's pulling us away from the center of the circle. So there's our Fg. So it's not helping, it's hurting, I guess, our centripetal force, if you want to say that. Now, we already figured this out, right? Mass times 9.8, and we got 49 newtons. What's pulling up? What's pulling this rock towards the center of the circle? It's the string, the force of the string, which we call T, tension. That's what we want to find. Now, let's get to the bottom of things. Now, our centripetal force, which is our net force, is equal to, now look at my diagram here. The tension is pulling up. Gravity is pulling down. All right, so that's what we got. Now, again, I can sub in our centripetal force here, but I already know that it is 49 newtons, right? We found it up here. At our, if we keep the same radius and the same speed, all right, this is our centripetal force. It's 49 newtons. So I'm going to put that in right here. Our tension at the bottom of the string, that's what we're trying to find out. How much tension's at the top, is at the bottom of the string. Because there's none at the top. All gravity's doing everything for us. FG, well, we already found that. That's 49. All right, well, if I want to solve for T, I'm going to move that 49 over to the other side. And so what I have is a 49 plus a 49. And that is our tension in the string. And that's why when you're wheeling something around, it feels you can feel the string pull, right? Where you don't need the string at the top because gravity's doing everything. Again, if you're at the exact minimum. And so again, 49 newtons, we get 98 newtons are in that. And so essentially what's happening with this string is it needs to supply 49 newtons to be the centripetal force. So we got the 49, and then we need another 49 to counteract gravity. The string does. All right. Again, I think I explained it a little bit different on my note that I did. This is I kind of worked. I try to improve every time. So this is a better explanation of what the heck is happening. All right. So, right, Nigel? Oh, yeah, he's not here. All right. So next up. Now, here's a great example. I love this example because it's real life. This is where this kind of stuff is used. All right. We have a car, 1,100 kilogram car, is making a turn. A nice little typo there. On a dry highway ramp, is experiencing friction. I hope so. The coefficient of static friction between the tires and the road is 0.6. Determine the maximum speed at which the car can safely negotiate a turn of radius 85 meters if the curve is not banked. All right. So the maximum speed, once you go past friction, because friction, static friction. Now, the reason I say it's static friction is because kinetic friction would work against the motion, the forward motion of the car. But in terms of moving towards the circle, the center, or moving away, which is most likely going to happen, that's where there's static friction horizontally in terms of your car, right? If you're looking at your car doors, either in the driver's side or in the passenger side, friction horizontally is equal to your centripetal force, is what's happening. Now, again, static friction. Again, kinetic friction would work against the forward motion. So where you're looking out your driver's side window or looking in your rear view mirror. So in this situation, again, I'm going to write down some of the information I have. I like to do that. Here's our mass of our object. We have 1,100 kilograms. So this is obviously some things that they plan on when they are building a road or building a curve. All right. Coefficient of friction or static friction. Again, I explain why it's static because we're looking at the horizontal, somewhat horizontal idea of this, which is 0.6. All right. We have a radius, which is 85 meters. All right. And we're looking for a velocity, how fast we can go before, your car skids out, which obviously can be affected by a lot of things here. Now, I'm going to draw a little picture of a car. Ooh, this is tough for me. Okay, I'll do here's my car. It's a block. All right, it's 1,100 kilograms, so we'll put that in there. Now, this car has gravity acting on it, right? But this car is not flying up into the air, not going into the ground. So that means the net forces top and bottom of this car have to balance each other out. And so we have a normal force, which is equal to our FG. Now, sideways for this car, so it doesn't skid off the road. This is out the doors here. You have a centripetal force, right? Now, that centripetal force is equal to the force of friction. Friction is doing all the work for you. If the road gets slippery, like today, right, where your coefficient of friction reduces drastically and your friction reduces drastically, well, then your centripetal force will reduce. And so you have a chance of being this guy right here, which I think I saw one of these guys today. All right, so our centripetal force has to be equal to the friction. As soon as the velocity increases, it's more than friction, and off the road we go. And so again, a formula for centripetal force, mv squared divided by r. Force of friction. We've had that formula before. It is our mu s times Fn, our normal force. Okay, so which of those do we have here? I always like to do that. We have the mass of the vehicle, right? We know the radius. We know our mu s. Fn, we don't know that yet. But our Fn, our normal force, is again equal to Fg, because that's why this car is not flying up into the sky or going into the ground. And so Fn is equal to mass times acceleration. All right, now I'm going to substitute in here. So let's see here. So mass is 1,100. All right, my velocity squared. The radius of this curve is 85. Equals our mu, our coefficient of friction here, static friction, which is 0.6, times mass, or Fn here, right, which I'm going to put m times g, which is 1,100, times 9.8. Now, I figured this out a little bit differently than I did in my note, and here's why. Because I wanted to show you something. I have 1,100 here, and I have 1,100 here. That's the mass. They're both on each side, so I can divide both sides by 1,100. They cancel each other out. This is a nice way of saying that in this situation, when we're talking about a road, it doesn't matter the mass of the car. It's irrelevant, all right? So that's when part of their calculations, they don't care about the vehicle, the mass. What they look at is the radius and the coefficient of friction here, right? Gravity isn't changing on Earth. So that's kind of the thing they look at here. All right, so I'm going to just simplify this. So I got v squared divided by 85 is equal to, let's see here, up here I got 0.6 times 9.8. So let's figure that out. 0.6 times 9.8. I get 5.88. Okay, again, I've said this many times. I got a number equaling a fraction. So I create a fraction equaling a fraction. So now I got 1 times v squared. Well, that's just v squared. And then I've got 5.88 times 85, which is 499.8. And of course, I'm going to square root both sides to find out our minimum velocity, which is equal to, let me see here, square root both sides, and I get, rounding to 2 decimal places, 22.36 meters squared. That is the maximum velocity in this scenario that you could go without skidding off the road. All right. Let me see now, just a little note. If I want to put this in kilometers per hour, you times it by 3.6. So let's just check it out here, just for curiosity's sake. That's about just only, in this situation, obviously this is not good, 80.48 kilometers an hour. And that would be the maximum speed that you could go before, again, your centripetal force exceeds the force of friction. So what do they do, right, to fix this situation? Now, I'm not going to do this example. I would do it if we were in a face-to-face class, not a virtual class, but I do want to show you this. Well, here's what they would do. You would bank it, right? This is why they bank things, because here's the thing. Not only would friction be working for you, but you would have a component of gravity that would also help you out. The more it's banked, the more gravity you would have. And again, that means that more centripetal force, because you would have a part of gravity going this way. So I don't know, I call that FG1, I guess. And you would also have your force of friction. So you've got not only your friction, but you've got extra gravity or a component of gravity working for you. And that is why they bank roads or racetracks, you could see, is so that your centripetal force would be greater. And that means you could go faster. All right. And so again, we're not going to go through that example, but I would do that normally. So if you see in